This is the Union Carbide plant in Bhopal, India. Its industrial footprint was integrated directly into the city's dense residential neighborhoods. The facility produced an agricultural pesticide marketed under the name 7. You can see the primary chemical components listed here on the packaging. Manufacturing 7 required the plant to store massive quantities of a precursor chemical known as methyl isocyanate, or MIC. MIC is a highly volatile compound. It reacts violently with water, generating intense heat and rapidly expanding into a gas. In December 1984, this specific chemical reaction occurred on a city-wide scale. Explaining the disaster requires mapping the gap between the plant's intended safety design and its actual condition on the night of the leak. To understand how thousands died in a single night, we must look at the facility through a reverse engineering lens, examining how a known chemical hazard was stripped of its required safety architecture. This is the primary storage vessel for MIC at the Bhopal facility, underground tank E610. To prevent pressure accumulation, the tank was never to be more than half full. The remaining volume was reserved for highly pressurized nitrogen gas. This nitrogen blanket acted as a physical barrier. The internal pressure was designed to prevent any external contaminants or water from flowing backward through the plant's pipes and into the tank. These were standard procedures, recognized globally for the safe handling of volatile chemicals. The safety of the entire factory relied on maintaining this pressurized equilibrium inside tank E610. By December 1984, the conditions inside tank E610 had deviated significantly from these baseline requirements. The tank was filled to 75% capacity, holding 42 tons of liquid MIC, far exceeding the manual safety limit. More importantly, the nitrogen pressure gauge had failed. The protective gas blanket was effectively non-existent. Plant records show that operators had been working with this lack of nitrogen pressure for 20 consecutive days. This state of neglect was a byproduct of plant-wide budget cuts enacted earlier that year, which had halted the replacement of critical gauges and valves. Before the leak began, the tank was already operating without its primary defense against contamination. The immediate trigger for the disaster was a routine maintenance task. Workers began a water wash of a nearby processing unit to clear blocked pipes. That processing unit was connected directly to tank E610 through a shared network of pipelines. A mechanical pipe stopper and a safety valve were in place to isolate the water. However, both failed to seal properly due to a lack of maintenance. Without the nitrogen counterpressure to repel it, the water flowed through the broken valves and poured into the tank. The contact between the water and the 42 tons of MIC triggered an uncontrolled exothermic reaction. The mixture generated intense heat, causing the liquid to boil and convert into a highly pressurized toxic gas. The resulting internal pressure was high enough to fracture the concrete casing above the underground tank. A routine maintenance task became the catalyst for disaster because the facility's engineering safeguards were no longer functional. The gas breached the tank's primary containment and was forced into the factory's external safety pipelines. It traveled first toward the gas scrubber, a device designed to chemically neutralize escaping MIC. The scrubber was offline and broken. The toxic gas passed through the system without being neutralized. The gas then moved toward the flare tower, which was supposed to incinerate toxic emissions before they reached the atmosphere. But a section of pipe leading to the tower had been removed for maintenance days earlier and was never replaced. The tower was non-functional. As the gas began to vent from the exhaust chimney, workers attempted to use external water hoses to spray the stack and knock the gas out of the air. The water pressure from the facility's hoses was insufficient to reach the top of the chimney, and the suppression attempt failed. For the gas to reach the city, 4 independent safety mechanisms had to fail in direct sequence. This chain of failure was the result of documented, long-term degradation across the entire facility. The toxic gas escaped from the factory chimney and began to drift into the night air. Because MIC gas is heavier than air, it did not dissipate. It sank to the ground and blanketed the city. Driven by the winter wind, this dense cloud moved directly into Bhopal's most crowded neighborhoods. The same chemical reaction that had occurred inside the tank now repeated itself within the victims. When the gas made contact with the fluid in the human lungs, it generated heat and tissue damage. This internal reaction caused fluid buildup and asphyxiation, killing thousands of people in the span of a few hours. The thermodynamic reaction inside tank E610 led directly to the physiological devastation in the streets of Bhopal. The mechanical record of the Bhopal disaster challenges the concept of an unforeseen accident. The data shows a volatile chemical process operating without its required engineering safeguards as a result of specific financial targets. When industrial maintenance and mechanical redundancy are treated as financial overhead, catastrophic failure moves from a risk to a mathematical certainty.